In this video, we will be doing code preparation for RNNs in order to preview the code that we will write next. As before, the main purpose of this lecture is to show you the syntax so that you are not surprised when we use it later. Now, whether or not you understand what this code is doing will be dependent on whether you watched the previous lectures. If you did, then you will know what's going on under the hood. If not, that's okay too. You can simply treat this like an API. Okay, so the first thing we will discuss is that the structure of this code is no different than what we had for ANNs and CNNs. You'll find that the setup for this video, meaning the previous conceptual lectures, is way more meaty than the actual implementation. Thanks to our hard work in the previous section, we already know most of what to do. The new parts are really just learning about the syntax for the new layers. So without further ado, let's review what we've already learned. We know that the first step is to build our model. The syntax for that is precisely what we will learn very shortly. The next step is to call the compile function. The arguments to this, such as the loss, will be dependent on what task you are doing, but it works the same way as before. The next step is to call the fit function. Notice that, like CNNs, xtrain and xtest should have the shape n by t by d. After training the model, we would like to use it to make predictions. Thus, we use the predict function, passing in the input data we would like to make predictions for. Okay, so this is exactly the same as before, as promised. Now at this point, since we've only discussed the simple RNN, that's what we will look at how to implement first. But what you will learn is that this is no different than implementing LSTMs or GRUs. You'll see that these other RNN units can be switched in and out with ease. By the way, remember that I'm not saying simple RNN to mean that simple is an adjective to describe the complexity of this kind of RNN. Rather, this is the actual name we use for this kind of RNN. In other words, we call this a simple RNN because that is its name, and I'm not saying it's simple as opposed to complex. So as before, the main thing we need to learn is how to build a model since all the other steps remain. In this case, it's helpful to think about how ANNs are built. ANNs are just a series of dense layers. So in the simple case, we have input, dense, dense. With an RNN, there is a self loop in the hidden layer. Thus, we simply switch the dense with the simple RNN object. And yes, it's just that simple. Self loop means simple RNN, and no loop means dense. One small note to make is that, for RNNs, the default activation is a hyperbolic tangent, although you can use other activations if you like. This is unlike the dense layer, where the default activation is identity. Now again, it's always good to think about the shape of the data as it passes through the neural network. So in this case, we start with a multivariate time series of shape t by d. This then goes through a simple RNN layer. As you recall, the simple RNN takes in a time series of vectors, x1, x2, all the way up to x big T. It converts them into a time series of hidden vectors, h1, h2, all the way up to h big T. Recall that each hidden vector depends on the current input x and the past hidden vector. By default, we only get to keep the final h of big T, which includes all the information from the past. In other words, the output of the simple RNN, by default, is an m-size vector, h of big T. From this, we pass this through one or more final dense layers, which is like a regular ANN. So supposing we have k outputs, our output will be a vector of size k. Now, as you recall, it's also possible to use an RNN such that it not only returns the final hidden vector h of big T, but all the hidden vectors of the time series. In order to do this in TensorFlow, we just need to pass in a single argument, return sequences equals true. By doing this, we get back all the hidden vectors in a single array of size t by m. So you can imagine this holding h of 1, h of 2, all the way up to h big T. From here, we have several options. So suppose this is a many-to-many task, where we want to have one prediction for every time step. So we want y1, y2, all the way up to y big T. In this case, we can just pass the output of the RNN through a dense layer, and this is what we automatically get. So in this case, the output of the neural network is T by K. Note that there is no special syntax you need to use. TensorFlow automatically knows that the dense layer should be dealing with a time series. In other words, the dense layer works for both single vectors and a time series of vectors. If you pass in a single vector, you get back a single vector of size k. If you pass in a series of vectors, then you get back a series of vectors, each of size k. The next scenario to consider is when you're dealing with the many-to-one task. In this case, we want an output only for the final time step. Now, of course, the easy thing to do would be to not use return sequences at all, and just keep h of big T. But let's suppose you want to keep all the hidden vectors, and take the maximum value over time. In this case, you can apply global max pooling, just as you would with CNNs. As you recall, this converts a time series of size t by m into a single vector of size m, completely eliminating the time dimension. Once we have a single vector of size m, we're back to the usual situation, and we can pass this through a final dense layer to get back a single vector of size k. The last scenario I want to cover is when you want to stack multiple RNN layers together. As you recall, the input of an RNN layer must be a time series, and therefore the previous RNN layer must output a time series. Of course, you already know that this can be done by setting return sequences equal to true. So here's an example of a many-to-one RNN where we've stacked multiple RNN layers. In this case, we start with an input time series of size t by d. Then, we pass this through one RNN layer with 32 hidden units. We set return sequences equal to true so that the output has the shape t by 32. Of course, this is still a multivariate time series, which can be passed through more RNN layers. So the next RNN layer also has 32 hidden units, but return sequences is now set to false, which is the default. So the output of this layer will just be a vector of size 32. The next step is to pass this through one final dense layer, where we get an output of size k. Okay, so I hope this was pretty simple. You've now seen how to stack multiple RNN layers together by using return sequences. Now, just as a little preview, I want to show you how easy it is to use LSTMs and GRUs, even if you don't know anything about how they work. Observe that it's simply a matter of changing the type of object that's being used. So if I want to use an LSTM, then I simply type LSTM instead of simple RNN. If I want to use a GRU, then I use GRU instead of LSTM. So in fact, you don't even have to understand how these RNN units work in order to use them. So if that's your preferred approach, then by all means, use that approach. So as with our previous study on CNNs, it is helpful to think about RNNs in terms of a more natural kind of input, such as a time series with length t and d input features. This is the same as when we studied CNNs, where we considered the input to be 2D images, even though we eventually used them for 1D signals, which we eventually thought of as word embeddings. Note that the same situation applies in this case. Initially, it's easier to think of inputs which have the shape t by d. This is just a time series of length t and d different measurement sensors. Of course, in practice, this won't be a time series we recorded using sensors, but word embeddings. As you recall, this is what we get when we have an input with sequence length t, followed by an embedding layer with embedding dimension d. The output of this is also t by d. Therefore, without loss of generality, we can always think of RNNs as having an input of shape t by d.